Hello, my name is Rodney Agnant. This is my 4th year in the program. Right now, I'm on my way to Caucasian University in the fall, so that's where we're starting. And I've been working with my mentor, Dr. Stephen M. Graham at St. John's University since my first year here. The name of my presentation is Conformational Analysis of Nucleosides. Alright, so what is cADPR? This is our target molecule for our study, and what it stands for is cyclic adenosine diphosphate ribose. It has different chains and veins that are able to move and organize themselves in different ways. And the ways that it organizes itself is called conformation. So that sounds a little bit complicated, but to break it down simpler, let's say you had 3 snakes, 3 green snakes, harmless, but they look exactly identical. Now you had one that was shaped like a straight line, one that was shaped like an S, one that was shaped like a circle. Now even though these 3 snakes were all identical, the same exact ways, they're shaped differently or they form different structures. So that's the same thing with our conformation. We can have different conformations of the small molecule, but in this end, it's still the same molecule. The reason why this is important is because this molecule, cADPR, is able to help regulate calcium release in the body, and that helps with the heartbeat. But then we think that if you had different conformations for this molecule, then that'll affect how well it's able to really help the heartbeat. So then 2 different examples are the north and south conformations. For the north conformation, there's this middle carbon bond that slopes up and to the left. But then in the other molecule, the south conformation, it slopes down to the left. This is more apparent when you overlap them, where it's obviously not the same. But also in the diphosphate chain, which is the red and yellow part on the left side, there are also some differences that occur. So then we have to look at these molecules in different ways. And this is basically the family that we have. We have our grandfather, Ciro, we have our father, Gaussian, and we have our teenager, Hyperchem. So let's say, we all love Grandpa or whatever, and he's a nice guy, and he's pretty knowledgeable. But the only problem is that when he doesn't watch the news, he doesn't know what's going on. This program that we have called Ciro is able to change proton-to-proton angles, change ribose ring angles into proton-to-proton angles. A ribose ring angle, if you look at the small diagram, has 4 atoms in it. It can either have 4 carbon atoms or 3 carbon atoms and 1 oxygen. But it stays within the ring, nothing sticking out. Now, if you have a proton-to-proton angle, it's going to have 2 hydrogens at the ends, but then it'll be connected to 2 carbons in the ring. So what we have are these 2 letters, A and B. We have questions? What's your question?
So these are organic hydrocarbons?
Yeah, these are all organic molecules. So what we have are these 2 letters, A and B, which are really important. A is a number that you're going to be multiplying the ribose ring angle by, and then B is a certain amount of degrees that you'll be tweaking that new number you have once you multiply it by A to get your new proton-to-proton angle. So this molecule is able to make that conversion, but it needs to have the A and B parameters already. So like we said, if you don't watch the news, you're not going to know what's going on. If you don't actually insert the new A and B parameters for your new molecules that you want to study, then Ciro becomes obsolete and you can't count on Grandpa anymore. So then we have father, Gaussian O3. So what this does is that it uses something called ab initio to calculate where the atoms should be. The thing about ab initio is that it's very precise, but it actually uses millions of equations to do its work. If you're using I won't say slow, I'll just say humble computer like mine at home, this can actually take from about 7 hours to a few days just for each conformation, and we run about 20 of them. So this is not it's not the best way to go about it if you're low on time. So we have our teenager, Hyperchem. Hyperchem, just like most of us, want to do things faster every day. So it uses something called electromechanics. The way electromechanics looks at molecules is that it treats every bond like a string. The more you pull on a string and the longer it becomes, the easier it becomes to pull on. Therefore, the longer the bond that you have, the weaker the bond becomes. So the purpose of the work that I did is that I want to see whether Amber 99 can be used for future studies to get those A and B parameters I was talking about before, rather than counting on using ab initio and doing days and days of work. We will actually compare these Amber 99 results to our ab initio results and Ciro. So we're actually comparing it to the 2 different generations, to the father, to the grandfather, to see if this is reliable. We can't use cADPR yet because even though it looks small on the screen, it actually is a pretty big molecule. So we use smaller molecules that had that rival string that we were looking at before, and we took that one rival string, which is RA, and then we changed it up a little bit into 5 other molecules, and we looked at all 6 of them. Procedure is a little bit complicated, but basically what we do is that for Amber 99, we use HyperChem to either take the molecule that's already in the database, and we use that, or we actually just tweak it a little bit so we can get the molecule that we need. Once we do that, we optimize it according to Amber 99. Amber 99 is just a force field that pushes the molecule to look like the way we want it to look. The only thing is that each atom, when sitting in its space, has a certain charge, and Amber 99 doesn't know necessarily how to say, oh, this is the charge we have. Especially, like, say you drew in a new atom, it's going to say the charge is 0, when if you learn later in chemistry, most atoms don't actually have a 0 charge. So we use ab initio just to calculate what the charge is, not where the atom should be. And that takes about 5 to 10 minutes, nothing extensive. After that, we use Amber 99 to re-optimize it just to tell us where the atoms should really be once we have the new charges. After that, we go on to the next confirmation, and we do 19 more after that. The reason why we do this is because we want to see a full cycle of change. Like, say we're looking at those 3 garden snakes again. It's like saying that we're going from the straight line to the S shape, to the circle, and then back to the S shape, and finally at the straight line, just so we can see all the changes that happen. At the end, we take all the rival string angles and proton angles, and we make a sheet of it. Also, we plot the energies of each confirmation according to each confirmation's name, just so that we can see which one's more stable, which one isn't. Like, say you had a brother or a younger sister, or let's say you had a few of them. One was 3, one was 5, one was 7. 3-year-old naturally has more energy. 7-year-old might start to become more laid back. So then the one with lower energy is actually more stable than 3-year-old. If you ask them all to sit down in one place for 5 hours, you'll be able to see what happens. So now we have our ab initio procedure, which is pretty much the same. We take our molecule that we use from the molecular mechanics, and we use these series of calculations called Hartree plot. The bigger the numbers and the more stars you have, the longer it's going to take and the more millions of functions the computer will be calculating. But once you set it running, you can leave the computer running and step away from it. And after that, we build the next confirmation upon next, just so we can, again, see that whole cycle. So for our results, I'm not going to show you all of them, but this is one of the examples for rivals, in which we got all the A and B parameters that we need for each torsion. This has some of the most extreme differences, in which we had a 13.4 difference between the A and B that we found using ab initio and the Amber 99 calculations for the 2' to 3' torsion. What that means is that if there's a 2', 3', those are the carbons that are there. You can see them in the blue. So if there's a 2', 3' torsion, it's connected to the first carbon, carbon 1, carbon 2, carbon 3, and carbon 4. That's the endocyclic or the rival string angle. The proton angle would be the hydrogens are connected to that second and third carbon. So H2, C2, C3, and then H3. For the 3' to 4 torsion, we see there's a 5% difference for the B parameter between Amber 99 and our ab initio results. But overall, what we find is that there's usually a 5% difference between Amber 99 and the results that we're looking at, whether it's from zero or from ab initio. So what this means is that we're in a great ballpark. We can actually use our rowdy teenager to do our work instead of having to spend days upon days waiting for ab initio to finish. Many of the fluoronucleosides, like those were the molecules that had names like F prime, DDA, we weren't able to find them in zero, so we actually had to refer to older research. But the older research is reliable, other scientists have tested it, so it was able to be compared. And we're now going to be using Amber 99 for our future molecules and use that to get the A and Bs that our grandfather doesn't have. All this information, unfortunately, is theoretical because it is being done in the computer. But this information, if found to be useful, will be really important because cADPR, when it helps regulate the calcium release, bonds to another molecule and then binds to something called the ryanodine receptor. Think of it as completing a key and inserting it into the hole, opening the door. So now the thing is that we don't know what that second part of the key is. We have a few suspicions, but we want to confirm what it is. So if we can make a better version of cADPR using what we've learned, then we'll be able to find what that second molecule it binds to is, and then we can learn more about how to prevent heart disease. Because we think that the second molecule, if it mutates, can lead to heart disease, and that's something that we don't want to happen. This is my bibliography. These are my acknowledgments, my mentor, Dr. Stephen M. Graham, the St. John's faculty, Dr. Sat, and the HCS staff. Thank you.